Okay guys, we're back. We're ready to start talking about the next section, which is the quantum model of the atom. And this is where it gets a lot more difficult in terms of it becomes very abstract, shall we say. So let's go. So the wave mechanical model of the atom was proposed by de Broglie, and it was an improvement over Bohr's model of the atom in that it explained things more than just hydrogen, and Bohr's model only worked for hydrogen. You should go into your book and read about both of those models because I am not going to explain them here. I think they're much better read than explained. The important points to me, however, is that instead of using an orbit like it did in Bohr's model, now we're using a probability map, and now we're going to call them orbitals instead of orbits. So it uses a probability map, which you can see here in the bottom left-hand side of our screen here. We have a defined area within this circle. 95% of the probability of finding an electron is within this volume. And remember, this is three-dimensional. It is not a two-dimensional, as you can see on the screen. And it did account for the wave-particle duality. And as you can see over here in this graphic on the left, or on the right, I'm sorry, the electron density is very high close to the nucleus, not right at the nucleus as it appears here, but very close to the nucleus, and then it decreases as you increase that distance from the nucleus. And so you should read more about the wave mechanical model of the atom as well as Bohr's model of the atom. So, in 1927, Heisenberg, who was a German scientist, I believe, proposed the Heisenberg uncertainty principle, and it involves the detection of electrons. And the Heisenberg uncertainty principle states that it is impossible to determine both the position and the velocity of an electron or any other particle. What that's saying basically is we're measuring the velocity of a particle. We cannot measure its position because by measuring its velocity, we change its position. And the reverse is also true. And so the Heisenberg uncertainty principle is coupled then with the Schrödinger wave equation, and Schrödinger's wave equation treats electrons as waves rather than as particles. And he did not take into account the idea that was emerging at this point that waves of only certain energies were allowed, but it ended up that those waves for electrons only came out, the only solutions that worked were certain energy levels. And so as a result of his equation, energy was quantized, not because he made it a condition, and so it was a very startling result. And quantum theory describes mathematically the wave properties of electrons and other very small particles. The only thing we're going to really be interested in is particles. Does this apply to baseballs then? Well, no, a baseball is not a very small particle, and so it would not apply to baseballs as it does to electrons. And so we have now orbitals instead of orbits, as was proposed by Bohr, and it is now a three-dimensional region where the probability of finding an electron is higher than some arbitrary value, which may be 90% or 95%, depending on how you're solving that equation. And so from here on out, we're going to talk about orbitals. And those orbitals are described by four quantum numbers. Those quantum numbers are n, l, m, and s. I'm going to describe each one, tell you what the values can be for those, and what they describe. So, first one is the principal quantum number, and it is symbolized by the letter n. And it tells you the energy level for that electron, or what row on the periodic table does it appear. Values for n can be any whole integer starting at 1. Our periodic table only has 7 rows, so you would think n can only go up to 7, and you would be incorrect. because just because we do not have an electron in that row on the periodic table doesn't mean the energy level for it does not exist. N can go up to any energy level. In fact, it could go to infinity. And that's when that electron has been removed from an atom. So N can be 1 through infinity. Second quantum number is called the angular momentum quantum number, which is symbolized by the letter L. That is not a 1, that's an L. And it tells you the shape of the orbital. And so it tells us whether it's round or is it some kind of circle or how does it look. And the values that we have for L can be 0 and could not be 0. And L can go up to n minus 1. So when n equals 1, L can only equal 0. When n equals 2, L can be 0 or it could be 1. When n equals 3, L can be 0, 1, or 2. So, if L equals 0, we have an s orbital. When L equals 1, we have a p orbital. When L equals 2, we have a d orbital. And when L equals 3, we have an f orbital. The next quantum number is the magnetic quantum number, and it is symbolized by the letter M, and it tells you the orientation in space. And again, those letters are L's, not 1's, and it goes from negative L to positive L. So if L equals 1, or 0, let's start with 0. If L equals 0, then M can only be 0. When L equals 1, M can be negative 1, 0, or positive 1. So there would be 3 values in that case, etc. And we'll talk about more of these in class, and you'll get sick and tired of them, but you'll get very good practice at how we do these. And the last quantum number is spin, and spin is symbolized by the letter S. It is a lowercase s, and it can have only 2 values. It can either be plus 1/2 or minus 1/2, and that symbolizes whether it's spinning clockwise or counterclockwise. So, I told you that L could equal 0 would be an s orbital. What does an s orbital look like? Well, here is an example. It is spherically shaped, and it is centered at the origin of the axes, and it is the first one that we run into. Then we can have L equal to 1, which would be a p orbital. P orbitals are kind of dumbbell shaped. They have 2 lobes on either end of the center of the origin, and then they are oriented on either the x, the y, or the z coordinate or axis. Once we start getting into L equal to 2, which is a d orbital, now we start getting some very bizarre shapes. We can have, as over here, double dumbbells in between the z, x, or y axis, or the y and x axis here, or along the x and y axis here. And then we get somewhere we have dumbbells with a ring. They're very kind of interesting shapes. And the last one we have possible is the f orbitals, which I haven't shown here. They get even more bizarre. We're going to stop here, and we will talk about electron configurations in the next video. Thank you.